So first lecture over spectroscopy. So organic spectroscopy. So what is the purpose of doing spectroscopy? So several purposes. For example, it can be used to determine the structure of a molecule. It can be used to determine the purity of a sample. It can be used to determine the composition of a sample. So what I mean by composition, that would mean like number of carbons, number of hydrogens, number of oxygens. So basically, what is the formula, empirical formula, molecular formula of a compound. And it can be used to learn some physical properties of a molecule or sample. So what do I mean by physical properties? So it can be used to determine dipole moment, three-dimensional shape of a molecule, electron densities, lots of properties of molecules can be determined using spectroscopy. And so if you're doing organic synthesis and you want to publish your synthesis and your results, then you will have to publish the following about your molecule. You're going to have to publish, well, this is not related to spectroscopy, but the percent yield. Related to spectroscopy, you're going to have to publish the proton NMR, the carbon 13 NMR. If it's chiral, the optical activity. You're going to have to determine the mass spec results. And as we'll see, mass spec can be used to determine the formula of a molecule, and it will determine the molar mass of a molecule. So if you want to prove that you made a molecule, then one way to prove that is the molecule has to have the right molar mass. So other things, you may have to publish the melting point of the molecule if it's a solid, the boiling point of a molecule if it's a liquid. Those, of course, are not spectroscopies, but NMR is spectroscopy, optical activity is spectroscopy, and mass spec is a form of spectroscopy. So if you're doing all this work in an organic chemistry lab doing synthesis and you want to publish your results, if you don't have good spectroscopy of your molecules, you're not going to be able to publish results because you'll use the spectroscopy to prove that you made the molecule, and you'll use the spectroscopy to prove that your molecule is pure. Okay, so there are many different types of spectroscopy. There's a mass spectroscopy. It's really not a spectroscopy, as we'll see. Oh, sorry, this should be. Oh, no, that's right. It's really mass spectrometry, and so I'll explain the difference in a little bit. So what does mass spectrometry do? It'll reveal the molar mass of a compound. And from that molar mass, you can use that to figure out the molecular formula of a compound. So obviously that's very powerful information if you can figure out the molecular formula of a compound. IR spectroscopy will allow you to figure out the functional groups. So it'll let you figure out if you have an OH in a molecule, so if it's an alcohol or an amine, if there's a C double bond O in the molecule, so whether there's a C double bond C in the molecule, so you can figure out if the molecule is an alkene or an alkyne. If it has a C double bond O, is an aldehyde or a ketone or a carboxylic acid or an anhydride or an acid chloride. So IR spectroscopy can be very powerful in that sense, but it's not going to really help you figure out the structure of a molecule, the exact structure, how every single thing is attached in the molecule. UV vis will reveal the conjugation. So if you have double bonds in a molecule, for example, so if we take these two molecules, which are structural isomers of each other, UV vis spectroscopy can easily distinguish between these two molecules. Mass spectrometry, not so easy to distinguish between these two molecules. Because these two molecules have the same formula and therefore same mass. IR spectroscopy, not necessarily ideal to distinguish between those two molecules because they both have carbon-carbon double bonds. I mean, there is enough difference in the molecules that if you're an expert in IR spectroscopy, you could probably pretty easily distinguish between those two molecules, but somebody who just has general knowledge of IR may not be able to distinguish between those two molecules using IR since they have the same functional group. But UV vis spectroscopy would be easy to tell the difference in those two molecules. NMR spectroscopy stands for nuclear magnetic resonance. So an acronym for nuclear magnetic resonance spectroscopy. Has nothing to do with radiation, not that type of nuclear chemistry, but it does have to do with the nuclei of the atom. So what does it reveal? It will reveal the carbon-carbon framework. So it'll tell you exactly how every single carbon in the molecule is attached to each other. And therefore, you also then figure out how all of the hydrogens in the molecule are attached as well. So that is extremely powerful. So to an organic chemist, NMR spectroscopy is probably without question the most valuable form of spectroscopy. Most people do an organic synthesis. If they don't have an NMR, they basically can't do NMR. They can't do synthesis. Okay, X-ray crystallography is basically like taking a picture. So it will show you, it'll basically show where every single atom is at in 3 dimensions. So then you can also will reveal exactly how every single atom is attached to each other. So there's all kinds of spectroscopies. There's circular dichroism spectroscopy, fluorescence spectroscopy, Raman spectroscopy, electron paramagnetic resonance spectroscopy, attenuated total reflectance spectroscopy. So all kinds of different spectroscopies. There's easily over 40 to 50 or more different types of spectroscopy. And in this class, the ones that we're going to look at, we'll look at mass spectrometry or mass spectroscopy, IR spectroscopy, UV vis, and NMR. For sure those 4, and if there's time we may look at some of the others like circular dichroism spectroscopy and fluorescence spectroscopy. So they're all very powerful. They all tell something different about a molecule. To an organic chemist, though, these 4 forms of spectroscopy are without question the most important and most valuable. Although X-ray crystallography is certainly perhaps one of the most powerful of the spectroscopies, since you basically get a picture of what your molecule looks like. The downside to that is to do X-ray crystallography, your molecule needs to crystallize. So you need to have a crystal, and so it needs to be a solid. And if it doesn't crystallize, then that makes it difficult to do X-ray crystallography. And furthermore, In the recent past, in order to do X-ray crystallography, you basically needed somebody who had a PhD in X-ray crystallography in order to run the samples, analyze the samples, and interpret the results. They are becoming a little bit more easy to use, so that you don't have to have a PhD in crystallography to do that anymore. But this is only recently with new technologies being developed. But most chemistry departments don't have an instrument to do X-ray crystallography because it's only been recently where it's been possible for the average user to be able to do X-ray crystallography. Okay, so what is spectroscopy? So a molecule will absorb electromagnetic radiation. If the energy of a radiation matches exactly the gap in energy between two states in the molecule. So what those two states are that can distinguish what the different types of spectroscopy is that's being done. Okay, so to follow up on this, so an important principle in quantum mechanics is that energy is quantized, and you can calculate the energy for transition using that equation, E equals h nu. So what does it mean for energy to be quantized? So we'll use a basketball example to distinguish between what is classical physics and quantum physics. So if you're playing basketball, for example, so you're shooting basketballs at a basketball hoop. So let's say that's a 6-foot hoop that you got set up for a child. So if you shoot the basketball this high. So in classical physics, can you make the hoop? And the answer is yes, because the basketball will just come down and go through the hoop. And in classical physics, yes, you can make the basket. In quantum physics, can you make the basket? And the answer is no. And why not? Because in the quantum world, if you want to make the basket, then you have to give it If you want to make the basket in the quantum world, you must give the basketball the exact right amount of energy that's needed for the transition. If you give the basketball too much energy, nothing happens. If you don't give the basketball enough energy, nothing happens. If you give the basketball exactly the right amount of energy, then it goes to the hoop and you've made the basket. So if we take a chemistry example, so if we had some atom, and we'll just use the Bohr model to represent. So we have our nucleus, and so we have an electron here in the n equals 1 shell, and you want the electron to go to the n equal 3 shell. So you want to do an electronic transition. So So let's say to do this transition, of course it depends on what the atom is, depends on how many protons and other electrons there are, but let's just say you needed electromagnetic radiation of, let's say about 400 nanometer to do that transition. Well, what if you used 350 nanometer light? That's more energy, right? Because this wavelength goes down, energy goes up. So if this has more than enough energy to move the electron from the first shell to the third shell, but will it happen? And the answer is no, electron will not. From n equals 1 to n equals 3, because the energy is not right. It doesn't match the exact energy gaps, so nothing's going to happen. If you shine the electromagnetic radiation of 350 nanometers on that atom, it basically just goes right through it. If that's the only thing that the energy could do is decide an electron from n equals 1 to n equals 3. It's not going to happen because it needs 400 nanometer light. That's basically what it means for energy to be quantized. So in terms of spectroscopy, for example, if we took a spectroscopy example, and we wanted to so if we demonstrate what it means for energy to be quantized using IR spectroscopy, so if we have an IR beam and shine it on a molecule, then basically what that can cause is it causes bonds to start stretching. So if this is of the right wavelength, so if it's of the wrong wavelength, or if it's of the right wavelength, so if it's of the wrong wavelength, then nothing happens. So let's get rid of that. So if it's of the correct wavelength, then the bond basically starts stretching, starts vibrating. So that would be an example of energy being quantized in terms of IR spectroscopy. If the IR beam is of the right wavelength, then that causes something to happen in the molecule, causes bonds to start stretching, causes bonds to start bending, as we'll see. But if the wavelength is wrong, then nothing happens. That IR beam just goes through the molecule, and the molecule doesn't absorb the energy at all. Okay, so the basics of an instrument. So how does an instrument work? So you have so EMR is electromagnetic radiation. So what do we mean by that? So it could be a microwave, could be IR, could be visible light, could be UV vis, could be an X-ray, could be a gamma ray. What did I miss? I probably missed one in there somewhere. But one of those electromagnetic radiations. And then you basically shine that through a sample. So we use this H nu to represent electromagnetic radiation or light. And so when we say light, we mean any of those forms of electromagnetic radiation. So if you shine that through the sample and the wavelength is wrong, then nothing happens. So the light comes out and hits the detector. And so the beam that comes into the sample is exactly the same as the beam that goes out of the sample. But if the wavelength is correct, that matches some transition state in the molecule, for example, it could match the amount of energy needed to stretch an OH bond. Then what happens is you don't get the light coming, can't spell. Then the light does not come out of the sample, and so now you take the difference. So you have a reference beam and you have a, oh no, that's that. That's different. Not that. So then you have a blank and a detector. So nothing absorbs in the blank, so the light comes out, but in the sample, if the wavelength is right, then the electromagnetic radiation does not come out of the sample because it's absorbed by the sample. And so now what you do is you plot this. So you would plot the intensity of the electromagnetic radiation versus the wavelength or frequency. So this would be 100% of the energy of the electromagnetic radiation is coming out, and at some wavelength the energy gets absorbed by the molecule, so not all of the energy comes out. Right, so you get a peak or a signal, and that just means the molecule is absorbing electromagnetic radiation. So your job now is to interpret that so that you can figure out something about the molecule. So depending on the wavelength of where that absorption occurs at, that tells you something about the molecule. Okay, so some spectroscopies are destructive and some are not. So mass spectroscopy is destructive. You put the sample in and you're not going to get the sample back out. So you have to keep that in mind if you only have a very little bit of sample. Of course, mass spec doesn't take much, but whatever you put in is going to be destroyed in the instrument. You're not going to get it back out. IR, UV vis, and NMR are non-destructive. So whatever sample you put in and study, you can recover it at the end. Okay, so in terms of instrument cost, so there's many variables that affect the cost of an instrument. Could be the source of the electromagnetic radiation. Some sources of energy are easier to produce than others. The hardware, the electronics involved. So one consideration is the instrument's resolution ability. So if we take a mass spectrometer, for example, there's two important categories. There's the low-res mass spectrometer, and those instruments can cost anywhere from about $10,000 to $50,000, and a high-res mass spec, and those instruments can cost $50,000 to $500,000. So what is resolution? So in mass spec, for example, the ability to tell the difference in molecules differing in mass. So at the minimum, the instrument should be able to distinguish species that differ by 1 mass unit, but that would be a low-res mass spec. Okay, so what do we mean by resolution? So if we have a couple of peaks in the sample, so those peaks would not be resolved. Whereas those peaks are resolved. So in terms of resolution, how it's defined. So the valley between the peaks should be no more than 10% of the height of the taller peak. So 1 mass unit resolution is obtainable on a low-res mass spec up to about a molecule with a molar mass of about 3,000 grams per mole. Right, so then this would be the height of the taller peak, and the height between the peaks, so little h over big H times 100 should be less than 10%. We're not going to be doing any things with these type of calculations, but just to illustrate to you the difference between the instruments. So if you want to distinguish between C16 H26O2, for example, which has a molar mass of 250.19328 grams per mole, and C15H24NO2, so if you add up the molar masses, This has a molar mass of 250.180704 grams per mole. So these differ in mass. Right, so this would be 1 mass unit resolution, so 250 versus 251, for example. In this case, the mass differs at the 100th position. So if you want to distinguish between these two molecules, a low-res mass spec is not going to do the job. You need a high-res mass spec. So you need a $50 to $500,000 instrument to distinguish between these two molecules on a mass spec. Okay, so how to calculate resolution? So we take a couple of examples. So we have a compound that weighs 2,999 and a compound that weighs 3,000 molar mass. Versus the one we just looked at, 250.180704 and 250.19328. So if we want to distinguish between these two molecules, so we need for these two molecules, we need an instrument that has a resolution of 3,000 over 3,000 minus 2,999 equals 3,000. So low-res mass specs can resolve molecules, can achieve resolution of 3,000. But if we want to distinguish between these two molecules, so 250.19328 over 250.19328 minus so if we wanted to resolve these two molecules on a mass spec so that we could clearly see the two peaks separately, if you can't see them, so if you did this on a low res, then you would just see the two peaks would merge together because the low-res mass spec can't separate them out, but a high-res mass spec could. If you have an instrument that could achieve a resolution that could achieve a resolution greater than 19,894. Okay, so we'll stop there. And next lecture we'll go into more depth in mass spectrometry.